Hey folks, I am in my car here because I'm working from home and it's kind of loud in the house with three kids. I want to talk about this problem using the Python control toolbox. So if you build this entire block diagram in Simulink, it's fairly easy to just make all these blocks, connect everything up, and just hit play and go. If you're using the Python control toolbox, unfortunately, you have to give the system all of the transfer functions and sort of combine them all together. So you do need to do a little bit of prep work by hand. And so I brought this into my Rocket book and sort of wrote it out, and then I'll bring it back into Python in a second. So if you look, you got the reference input, this HR coming in, and then summer, the error, a controller I call C. You'll see down here I call this C. The control input to the plant I call G. And then there's a summer over here where a disturbance hits a disturbance transfer function I call D. And then that goes out to Y, which is your desired speed. And then that comes back to a feedback sensor block, HY. And then that shoots up here to the top. So before you can, like I said, pull this into a Python, you need to bring it down into one block so you can see what's going on. Now, this would all be really easy if W was 0, because then you could just close the loop and you could do CG over 1 plus CGH and you'd be done. Unfortunately, you can't do that because you have this summering block here. Now, there are some tricks that you can do where you can like move this outside the loop and then close the loop and things like that, but I don't like to do that. So what I'm going to do here is I'm going to write everything out in equation form here. So if you look at Y is X plus WD. Now, W is the input, and D is a transfer function. So if you just multiply those two together, you get WD. So Y is X plus WD, and so X is Y minus WD. You just bring WD to the other side. If you keep going, let me not show you too much here. If you look at the error is RHR, right? So R times HR gives you this right here. So RHR minus Y times HY. Now, if you look at X over here, X is CG, right? If you just combine these two blocks, this is G and this is C, you're going to get CG times E. But E is this here, so you can substitute that into here, and so you get CGE, which is now RHR minus HYY. And then if you take this up here for X and substitute it down in here, you're going to get Y minus WD on the left for X, and then the right-hand side just comes in. And then what you can do is you can bring the Y over to the left-hand side and then substitute, factor out the Y and then divide. And what you get is RHR, this transfer function here, plus WD, this transfer function here. And what you notice is that this is actually G closed loop without the disturbance, right? If you go back into the transfer function, CG over 1 plus CGHY is this right here. And so what happens is that you can actually write an equivalent transfer function like this, or block diagram, where you have RHR coming in here, WD coming in here, and then it hits G closed loop. And both of these are equivalent because you can just bring G closed loop into the other side. So like I said, there are some tricks you can do where you can bring this outside and close the loop and things like that. But in my opinion, it's way easier to do this. Okay, so now that we have this, we can bring this entire thing into Python. And so I have a script here, problem 4.27.py, and I'm going to upload this to my Python controls Git. What I want to do first is simulate the open loop. So first what I need to do is I need to get these transfer functions in here. So C is KP. So for now I'm going to make KP equal to 1. I need HR. I'm going to make HR 3 and HY 4. And then I'm going to make, let's see, A, I'm going to make 5, and little a, I'm going to make 2. And then I think that's it. So now I can make, okay, wait, these are transfer functions. These up here, these are constants. I'm going to make B equal to A. Should I make B equal to A? Now let's make B different. B is 6. Okay? And so now I can, so these are, I'm going to call these constants. And then down here, I'm going to call these transfer functions. Okay? So there is CHR, and HY. Okay? And then my G is, I actually have to use the transfer function toolbox. It is A, 1 little a. I'm going to print G just so we see what we're dealing with. And then D, the disturbance transfer function is B over 1 comma A. And I'm going to print D. And I'm going to run this just to make sure we got everything right. So there's my plant dynamics, and then there is my disturbance transfer function. Okay? Now, according to this problem, they want us to simulate the open loop system first. Okay? So let's simulate the open loop system would just be this whole row here. So it would be HR times C times G would give me my output. And then it also says that R is a step with a desired speed of R naught. Okay? So let's make some constants. My desired speed, I'm going to say, is 15. And what I need is my G open loop. And that's going to be let me make sure I got this right, HR times C times G. Okay? And then I'm going to simulate this for, 10 seconds. So that says 0 to 10 seconds, 1,000 data points. And I'm going to say T out, Y out is CETL. Oh, and then by the way, I guess I didn't say this. This is the control system toolbox in Python. So control as CETL, that is the control system toolbox. This is the plotting toolbox. And then this is the numeric Python toolbox. These are all the toolbox. In MATLAB, you just kind of have them all installed automatically. So it said here that the reference command is a step. So I'm going to hit it with a step. G open loop, but I need to scale the output by R and do times equals R naught. When you do step response, this assumes that R is 1, but that's not true. R is R naught. Sorry, little r is 1. But we need to scale the output by R naught. So we have to times equal, which just says take the vector and multiply the whole thing by R naught. So if we do plt.figure, which makes a new figure, and then plt.plot, T out, Y out, and then plt.show, we should see the open loop response, okay? And it went all the way to 105, okay? Why did it do that? Well, let's print G open loop. There's G open loop. It's 15, the final value of G open loop is 15 over 2. So if I take the final value, 15 over 2, and then multiply that by R0, I get 112. So that means that open loop, my system like overshot like crazy, okay? So unfortunately, if we want to get this to have no steady state error, we need KP to be, let's see, little a divided by big A divided by HR. So let's do that over here. So let's take KP, and I'm going to move this down here, and I'm going to say design my controller, and I'm going to put KP is, what did I say? Little a over big A times HR. And I'm going to print KP equals KP. Okay? And what do I get? KP is 0.133. And you look there, boom, open loop, the system responded great. Okay? So now let's look what happens when I close the loop. Okay? Now, here's one thing that I didn't discuss. If you look at, even if there's not a disturbance, if you close the loop, if you look at Y is scaled by HY, and then it's subtracted by HR, which is scaled by, R, which is scaled by HR. If you subtract these two, if you want to subtract the same thing, you need to make sure that HY and HR are the same. Now, I'm assuming that HY is part of the sensor, and I can't touch HY, but I can change HR. So I'm not only going to design my controller, but I'm going to design my command generation block, and I'm going to let HR equal HY. Now, unfortunately, because I did this, I need to move this up top, okay? And now HR is equal to HY, KP is going to change accordingly, and so now KP is 0.1, my system still gets to the desired 15, but now my system is operating in a scenario where when I close the loop, everything's going to shake out properly. It didn't matter before because I wasn't closing the loop. So now let's close the loop, okay? And let's do this without a disturbance. So close the loop without a disturbance, okay? Now all I need to do to figure this out is go here. All I need to do is to set this entire term to 0, and the closed loop transfer function is CGHR over 1 plus CGHY. And I have all the transfer functions for that. So G closed loop is just HR times C times G over 1 plus C times G times HY. Okay? And let's see what happens. T out, Y out, closed loop is Seidel dot step response. I'm still going to hit it with a step. T out. And then I'm going to do, I need a scale. I still need a scale by R0. So Y out, closed loop times equal R0. And then PLT dot figure, PLT dot plot, T out, Y out. Okay? And then PLT dot plot, I don't want to plot, I want to show. And I need to plot the closed loop, okay? So let's take a look. So it looks, boom, so it looks like everything's great, okay? I still got to 15, so that's all good. And open loop and closed loop, I still got to 15. So let's do a couple things. Let's plot this on the same figure. So I'm going to get rid of this PLT dot figure and get rid of this. And I'm going to throw in a label here and say closed loop, and then plt.plot t out, comma y out, and label open loop. Okay? And then I'm going to do plt.grid, plt.legend, plt.xlabel is time, plt.y label is speed in meters per second. Run that, and everything's well and good. So with no disturbance, my open loop and my closed loop systems do exactly the same. Now what's interesting is that I didn't get any steady state error. Now why didn't I get any steady state error? Let's take a look at that. If I print the, oh, that's because I did, oh man, I thought everything was great. Okay, now everything's going to screw up. Oh, bother. Okay, so the open loop went to 15. Closed loop system, unfortunately, has steady state error. Why does it have steady state error? Well, let's take a look at this system. The type of this system is 0, and the type of this system is 0, which means the type of the top row is 0. If HY is also 0, it means the type of the entire system is 0. And we know in the table that if you hit a type 0 system with a steps response, you are going to run into a situation where the steady state error is going to be non-zero. The only way to get rid of steady state error completely is to increase the type of the system, which would mean moving from proportional gain to integral gain, which we can't do because that's not in the problem. Or we can just make KP really, really, really big. So we have a couple issues with this. If we make KP really big, so I'm just going to multiply by 1,000, right? My closed loop system is going to be down here, but my open loop system is going to freak out because I'm scaling the output, okay? If I just don't plot the open loop system anymore, you'll see that I'm getting really, really close to 15. I'm also like crazily increasing the time constant, right? I mean, I'm making this system like respond super quickly. So we don't necessarily want to increase KP like crazy, okay? Maybe we want to increase it a little bit, but we don't want to go too much. Okay, so then why do we have the controller in the first place? Like, why don't we just leave it like this? Well, let's talk about what happens when you hit the system with a disturbance, right? Well, if you go back to my derivation, open loop, what we really plotted was this times this times this and simulated this, but we didn't add this disturbance here. So really all we need to do in order to get this to work for the open loop system is say T out, I'm going to call it WD out, is Seidel.step response. And again, it's a step. In this case, Let's see. Whoops. That's a picture of my kids. Um, let's see here. I'm trying to find the textbook pages. I apologize. I'll probably edit this out. Okay, here. So it says what happens if W is W naught over S. So what we need is a W naught. So I'm going to come up here for my constants, and I'm going to make W naught equal to -3, right? We have some disturbance that's -3, okay? Let's see what happens if we do, it's a step, so we just need to do D and T out, and then we need to scale WD out by W naught. So we're going to say WD out times equal W naught. And then what we're really dealing with is that we actually didn't simulate Y, we simulated X. So I'm going to go back to Tony and I'm going to call this X out and this X out. And then I'm going to say that when I plot, I'm going to call this X out, no disturbance. And then Y out, well, what's Y out? Well, Y out is just WD out plus X out. So then I can go ahead and plot plt.plot T out, Y out, and say open loop with disturbance. Okay? Then I need to do the exact same thing for this guy. So this was really X out closed loop. I need to simulate WD out closed loop, which is Seidel.step response. And it's equal to, I need to go to my derivation here. It's D times the closed loop, right? So the first one was HR times closed loop, right? So what I actually want is I want to get rid of this and make this closed loop, bring the HR here, and then this is going to be D times G closed loop, comma T out. And then again, I'm going to scale the output. So WD out closed loop times equal W naught, and then Y out closed loop, scale it by R naught, and that's X naught, X out. And then I'm going to say X out closed loop, this is closed loop, no disturbance, and then plt.plot T out, comma, Y out closed loop, this is closed loop with disturbance, okay? And let's see what happens here. It's going to throw an error, of course, because I didn't. Y out closed loop is X out closed loop plus WD out closed loop. Okay, so let's look at what we have here. The green is open loop, no disturbance. And if you look at the green with no disturbance, we get to 15. Everything's great. The red is open loop with the disturbance. It goes all the way down to 6 because you're not looking at any feedback. Now, this one here, this blue, is the closed loop, no disturbance, and you might say like, hey, you've got a lot of steady state error, dude. But when you add this disturbance, it barely moves. So really all we need to do is increase our KP. Now the problem with increasing KP, like I said before, if I take KP and I do times 1,000, let's say times 100, all of my closed loop stuff is going to be down here and all my open loop stuff is going to be up here. So really what we need to do then, if we're going to scale by 100, is we need to say like, okay, let's design this differently. Well, actually, I'm just going to get rid of the open loop completely because, you know, the open loop's not going to work anymore. So I'm just going to get rid of it. And when I plot that, look at that. So now you have a situation where you almost have no steady state error because your gain is so high, and you do pretty well rejecting it. And there you go. So that is at least the beginning of the project. There is more to the problem. I think there's a part B and a part C in there. I should have just downloaded this. There it is. So there's a part C. Oh, I guess I did part C, but you kind of need to explain this. There's also, I may have said don't do part D, so I may have done the entire project, but you know what? School's shut down right now, and I'm trying to help out as much as I can. I hope you enjoyed this video, and I hope you enjoyed this screencast. If you have any questions, post them in the comments.